Hello everybody, I hope you're having a wonderful day and you're ready to do some more math. We're looking at the Euclid competition from the year 2003. We're all the way up to question number 8. We only have a few questions left to go, so let's dive right in and take a look. So question 8's got two parts, both of them written, as we can see with the little symbol beside the A and the B, the handwriting on paper. And part A, a circle with its center on the y-axis intersects the graph of y equals the absolute value of x. So this turns positive numbers into positive numbers and negative numbers into positive numbers as well, and keeps their values essentially the same. So it intersects at the origin and exactly two other distinct points, A and B, as shown. Prove that the ratio of the area of the triangle ABO to the area of the circle is always 1 to pi. Okay. I'm going to redraw the picture while I start trying to think of a plan of attack here. I'm going to need another piece of paper. Okay. I should have drawn the circle first, but that's okay. Well, I've drawn worse circles in doing other math today, so I'm going to stick with that one. So we have an intersection point O at the origin, and we've got our absolute value function. Okay. We've got A over here on the positive side and B over here on the negative side. So we're told that the center of the circle, I believe, center of the circle is on the y-axis, so let's give that a name. This length here would be the radius, so let's call this 0r. Okay. So from there we could probably work out the equation of the circle and then ask it to intersect with y equals the absolute value of x. And we could probably work out points A and B in terms of r. Will this help us? I think it probably will. But I'm just thinking I think there's another way to do this. This angle here is a right angle, and so if I connect up A and B, I've got a chord that subtends a right angle. That has to be a diameter, and so it has to pass through the center here. And I think then that's got to be R, and so then A's got to be RR. And then B will have to be negative RR. This is 2r, it's got a height of r, as we've already noted. So we could work out the area of the triangle, and then we'd also know the area of the circle, because we've got r. So I'm going to actually just do that, instead of working out A and B by doing an intersection. So observe that angle AOB is 90 degrees. How best should I justify that? I would say probably the best way to justify that is by saying each of these is 45 degrees. So the angle that this makes, that y equals the absolute value of x makes with the x-axis is 45 degrees on both sides. Okay. I would say that's a decent justification. You could probably go a little further into it by saying, well, any point on here is going to look like xx. And so if we make a right angle triangle, we'll have x, x, and so it's got to have 45. So if you're not satisfied just saying, well, it's 90 degrees because it's what's left over because you got two 45s, justifying each of those 45s isn't particularly difficult, and so that would give you a little extra security if you were worried that you weren't providing enough to get the marks. And that's okay, and that's a valid concern. But I think what I've written is enough to justify the 90 degrees. Okay? So AB is a chord of the circle which subtends, or is subtends when the angle, which is subtended by a 90 degrees. Angles subtending the same chord, so yeah, which is subtended by. Got to make sure the verbs go in the right place. So it's got to be a diameter. This is a nice circle fact that you can employ. If you've got a right angle triangle and all 3 points lie on a circle, then then the hypotenuse has to be the diameter. And if you're looking at a diameter and you've got if you're looking at a triangle and all 3 points are on the circle, and one of the lengths happens to be a diameter, you know that that's going to be a right angle triangle. It's a back and forth statement, and it's incredibly useful. Okay. So it passes through the center of the circle at 0r, where r is the radius. Okay. So as I said, from there we can see do I need to justify that at all? Just trying to think, is it obvious that it's RR? I mean, couldn't somebody come along and say, you've got your circle, it goes like this, but A is up higher than B, who's lower? Well, what can... Either this is really obvious, or I do need a justification here. I want to show that this is a right angle, because that would do it. That's 45, that's 45. I guess it's not entirely obvious. I like brevity in my solutions, but I can't just jump all over the place and say, well, this is obvious, this is obvious. So let's redraw our diagram. I'm breaking down. I'm gonna just so not from there we can see. Let's redraw our picture, and let's justify this. No, unhappy with that. Very unhappy with that. Let's draw the circle first. Go through its diameter. Okay. So here's our A, here's our B. There's the origin, and we'll call C the center. And that I know is at 0R. Of course, the origin is at 0, 0. So I know AB is a diameter. That's great. And I've already said these guys have to be 45s. And this one has to be a 90. Okay. But there's no reason right now that those two, the angle at B and the angle at A, have to be 45s. I want to justify that. So I know AC has got to be the same as BC, has got to be R. That's fine. And so RR and negative RR clearly do work, but I'd like to be able to justify that a little bit more. So let A have coordinates AA. I was trying so hard to avoid using the equation for the circle, but A minus 0 squared plus A minus R squared has got to be R squared. And that actually already shows us that both of these have to be R. That both AC and BC have to be R, so we haven't gained anything new there. Can I just say by symmetry? I think just saying by symmetry would work, and that would avoid all this nonsense. Because clearly the picture is going to have to be symmetrical. Because otherwise, suppose it weren't symmetrical. We've got our circle, it intersects here. This isn't the best. But say it weren't symmetrical, and this point here were definitely lower than this point up here. This graph is symmetrical, so there should, and the circle is symmetrical about the y-axis. So if I were to flip it, I'd have the exact same picture, but then in this case, A would be up higher than, or B would be up higher than A, and that wouldn't work either. So by symmetry about the y-axis, must have the same height. I'll even just leave this picture in for justification, but I think this statement stands on its own. So A and B, in order for the line between them, if they both have the same height, then AB must be parallel to the x-axis and since it passes through 0r, they must have y-coordinate r. So therefore, A is going to be RR, and B is going to be negative RR. Not that hard to see after that point. So I think that's justification of those guys. That's fine. So that means AB is perpendicular to OC, C being the center there. And since that's the case, OC is equal to R, AB is equal to 2R. So triangle ABC, or sorry, AOB has area of 1/2 base times height, which is going to be R squared. And the circle has area pi R squared, giving us a ratio of pi R squared to R squared, which is just pi to 1, which is exactly what they asked for. Okay. And that was just A part. Now we've got B part. It's also got a circle in it. In the diagram, triangle ABC has a right angle at B. Okay, so we're looking at another right angle triangle. And we got M is the midpoint of BC. A circle is drawn using BC as its diameter, so M would have to be the center. P is the point of intersection of the circle with AC. That's fine. The tangent to the circle at P cuts AB at Q. Prove that Q connected up with M is parallel to AC. Okay. So prove that they're parallel. So, a couple things I could see to show that something's parallel. I'm going to redraw this picture, and then I'm going to label it with different possible plans of attack. Right angle. There's M. There's P. There's my point of tangency. There's my external point. Now, immediately as I'm drawing this, alarm bells are going off about power of a point and tangency stuff. As soon as I see P and its tangent, I automatically want to connect it up with M, and I'll do that in a moment. But I want to finish labeling this and saying, okay, QM. I want to show, I'll use blue for that one, I want to show that that's parallel to AC. So one way I could do it is maybe drop a point here and show that these are right angles. I think that would do it. Another way I think we could do it is we could show that this angle and this angle are the same. Because two lines intersecting a third line, both at the same angle of incidence, must be parallel. We could also do the same thing up here with these two. We'll use a different color here for a moment. If we were to show that those angles are the same, we'd be all set. Okay. So, those are possible plans of attack. But right now I'm going to draw in this right angle. So since P is a point of tangency for PQ, that line there, then PM must be perpendicular to PQ. Okay, this is another nice circle result. Just like with that, it's got to be the diameter if it's opposite a right angle inside a circle. Just like that, we have this nice point here. Okay. Now, both MP, MB, actually, don't just say that because we also have MC. As they are radii, not diameters. M is the center, as it is the midpoint of BC, and that's the thing we chose to be the diameter when we made the circle. Okay, so we've got, we'll use yellow here, we've got these guys, and they're all the same. Okay. Now, we've also got right angles here. And these lengths here are all the same, and I think, yeah. So, since MP is equal to MB, and MQ, of course, is equal to MQ, and angle MPQ is equal to angle MBQ, then it follows that triangles MPQ and triangle MBQ are congruent. Okay, they have a length in common. They have two lengths in common and another angle in common, so it's got to be the same. So using Pythagoras, we could show that QP is the same as QB. Then these would be two triangles that have the same side lengths, and that's definitely congruency. Okay, so knowing that, we have, well, this green angle is duplicated, so we've got two green angles and one green angle. Not seeing anything right there. And then we've got this red angle is the same. And so, sorry, we don't know this green angle, we don't know that this red angle is here. But I can show that this angle's got to be the same as this red angle, because we've got, well, we'll include the point here, PB. Okay, so I'm actually going to have to redraw this picture to illustrate this over here. Okay. So whatever angle is up here, subtending PB, double its angle will appear subtended by the center. And this is what's known as the Star Trek theorem. Because if we have our chord subtended by this point and this point, we got a dot here, we got two dot here, but it looks like sort of the Star Trek communicator pin badge. Okay, so that's why it's called the Star Trek theorem. And there's a nice proof of it that this is R, this is R, this is R. So they do the same thing there, and then so this dot and this dot are the same, and this dot and this dot are the same. And so if we extend this line through here, exterior angles, we've got to have two dots, two purple dots here and two green dots over here, and so together they make up twice that angle. So it's quite nice, quite useful. It's called the Star Trek theorem. There might be a better name for it, but I don't know it. So we can even say by the Star Trek theorem, but This guy up here is C. Since C and M subtend chord PB, and M is the center, and C lies on the circle, then the angle at C, so angle PCB, must be 1/2 of angle PMB. But this is 1/2 of, if we add in Q again, this is 1/2 of twice QMB. So that angle is the same as that angle. So since AC and QM intersect BC at the same angle, we can conclude they are parallel. So each of these was the red angle, and this guy must be half of two red angles, so he must also be the red angle. And that's what has finished off the proof for us. Okay, we got more of the Euclid to go, so we're going to flip the page. And we're going to just go back and just take a gander at 9 for a second. Take a deep breath, and join me in the next video. We're going to look at 9 together.